Welcome to the fifth week of this discrete mathematics course. So this is the first lecture in the fifth week. We have been looking at various proof techniques. In the last week, we saw some induction, which is one of the most powerful proof techniques for proving theorems in discrete mathematics. So we'll continue with this particular proof technique and see how much more can induction help us proving more complicated theorems. So to quick recap, so we have been trying to look at statements like A implies B, and to prove such a statement, we have seen there are quite a number of proof techniques, namely constructive proofs, proof by contradiction, proof by contrapositive, induction, counterexample, and so on. We have now almost covered most of it, and we have been studying the proof by induction. So we started our whole study of proof techniques by looking at how to split a problem into smaller parts. We took the help of propositional logic to prove that for certain cases, splitting up the problem into smaller parts can be possible. So one of them is in the case of when you have to prove A implies B, B is written as C and D. In that case, we can split up the problem into two smaller parts. Similarly, we saw that removing redundant assumptions is something very useful in getting a simpler statement of this problem, which can be easier to prove. And then we also looked at some examples where proving something stronger is easier. Right? In the different proof techniques, we have seen constructive proofs. Namely, particularly we have looked at direct proofs where you work with A and end up proving B. And while this can be sometimes be magical, we can do a backward proof, namely first work with B, simplify it to some other form, say C, and then maybe proving A implies C can be easier. We also saw some case studies in which you can split the assumptions into a finite number of cases, and for each case you prove it separately. That is, if A can be written as C or D, then you can split up the problem A implies B as C implies B and D implies B. Then there was also the proof by contradiction. The idea is that instead of proving A implies B, one can also prove not B and A is false. Sometimes this is a different way of looking at the problem and can be easier to solve than A implies B. Another particular technique is instead of proving A implies B, one proves that not B implies not A. They are similar statements or equivalent statements, and this can be useful particularly when B is of the form C or D. So these were the various proof techniques that we saw. One more proof technique that we were kindly going on. One more proof technique that was we also saw a proof technique called counterexample, where if we have to disprove a theorem or statement A implies B, the idea is to produce a proof that A doesn't imply B, or in other words, if the problem is of the form for all x, Ax implies B, and we have to prove the negation of it, which is there exists x, Ax not imply B, which in turn becomes there exists x such that Bx doesn't hold and Ax holds. So this is what we call as the proof by counterexample. Other than this set of proofs, we also looked at the proof of induction, and that's what we have been doing for the last week. The idea is to again split up the problems into smaller problems, but here we split up the assumptions or the set of the situation in which we have to prove the theorem. We split up into possibly infinite number of subsets. So in other words, this will imply that this A implies B gets split up into infinitely many problems. Now usually the subproblems are indexed by some parameter of the input. So the A implies B does become something like P1 and P2 and so on till infinity. So thus the problem A implies B boils down to a problem like this: for all k greater than or equal to 1, prove that Pk is true. Unfortunately, we cannot solve all the Pi's individually because there are infinite number of them. So we take the help of mathematical induction, which helps us to solve all of them at one shot. The idea is simple. First prove that P1 is true, then prove that if for some k we prove Pk is true, then using that prove Pk plus 1 is true. If we can prove that, then the Pn is true for all n. Now this is quite an accepted in principle, though to ensure that correctness of this principle, we do have to use or write a new axiom, which we call the principle of mathematical induction, which states that this statement or this way of proving it is a valid proof. Now there are different versions that one can use of this particular case. We have already seen some of the versions. So the version 1 is the case which we just discussed, which is that if we have to prove that for all k greater than or equal to 1, Pk is true, then we have the first proof that the P1 is true. We call this one the base case. Then we have the induction hypothesis, which says that let Pk be true for some k, and the inductive step is assuming that the induction hypothesis is true, prove that Pk plus 1 is true. Now there is another version that we saw, which is the case that for k, if you have to prove that for all k greater than or equal to r, prove that Pr is true, then we just shift the base case, namely we prove that Pr is true, and assuming the same induction hypothesis, can we prove that Pk plus 1 is true, assuming Pk is true. And once we prove that, it helps us to say that for all n greater than or equal to r, the problem Pn is true. We also looked at another version, the third version. This one was the case when we have the same kind of condition where we have to prove that for all k greater than or equal to r, Pk is true. So instead of having the base case as Pr, we can have the base case as Pr and Pr plus 1. And then we can have a slightly weaker induction hypothesis, induction state. So namely, the induction hypothesis is saying that Pk is true for some k greater than r. All we need to show is that assuming that Pk is true, prove that Pk plus 1 is true. As I told you in the last video also, the idea is to ensure that every possible points are getting proved. So for example, if say this is R, the base case says that okay, I know how to solve R, I know how to solve R plus 1. Now the induction step will say that okay, if I know R, I know how to prove R plus 2, If I know r plus 1, I know how to prove r plus 3, and so on. And you can convince yourself that we will end up proving all the points greater than r. So in other words, this technique will help us prove that for all n greater than r, the problem Pn is true and hence proved. Now, one thing to remember here is that already we have seen this version 1, 2 and 3, particular version 2 and 3 solves the same problem for all k greater than or equal to r. Now, which version to use? Now, which version to use of course depends on the problem. For some problems, applying the version 3 will be easier, meaning proving k plus 2 is true assuming pk will be an easier thing. In some cases, proving pk plus 1 is true assuming pk will be an easier thing. And in that case we use version 2. So, which version of induction hypothesis to use depends fully on the problem in hand. Now there is a zillion more versions that can be done. I will give you one more version here. For the same problem, where for all k greater than or equal to r, we want to prove pk is true. Now, we have the same base case that when we prove that pr and pr plus 1 is true, we have the same induction hypothesis that the induction hypothesis changes here. Instead of having the hypothesis that pk is true, we assume that both pk and pk plus 1 is true. And using that, can you prove that pk plus 2 is true? Right? If we can prove that, again that will solve our whole thing. Let's try to see how we can ensure. So if this is r and this is r plus 1, the base case says that we know how to prove r and r plus 1. The induction hypothesis says that, okay, since I know r and pr plus 1, so I will be knowing pr plus 2. Now again, since I know pr plus 1 and pr plus 2, I will be knowing pr plus 3 and so on. Thus, this way continuing, we would be able to prove the pk for all k greater than or equal to r. So this is also a valid induction hypothesis. Right? So let's see how can one apply this particular version. Say, let's look at this particular problem. So an is a sequence of numbers such that a1 is 5, a2 is 13, and we have been told that for all n greater than or equal to 1, an plus 2 is equals to 5 times an plus 1 minus 6 times an. Then prove that an is equals to 2 power n plus 3 power n. Now, as we have done in other cases also, we have to split them up into smaller cases, right? So here, of course, let pk be the case that if an is the sequence, then ak is 2 power k plus 3 power k. And we have to prove that for all k greater than or equal to 1, pk is true. Right? Now, okay, if I have to solve this problem now, what do we have to do? We have to do these three cases. The base case, which is say we will prove P1 and P2 is true. We will have the inductive hypothesis, which will be let Pk and Pk plus 1 is true, and using that we will be proving Pk plus 2 is true. So the base case is that we have to prove that A1 equals to 2 power 1 plus 3 power 1 and A2 equals to 2 square plus 3 square. And this is not that hard to prove because it can be checked or verified easily. right? So now in the induction hypothesis, we have that, let's assume that, remember what was Pk? Pk was Ak plus 1, so this one was Pk, and this is Pk plus 1. So we have that Ak equals to 2 power k plus 3 power k, and Ak plus 1 is 2 power k plus 1 plus 3 power k plus 1. And what we have to do is that, assuming the induction hypothesis, we have to prove, of course, this statement, which is Pk plus 2. Now let's see how can we solve it. Now quickly recall that we were given this particular recurrence relation. We were given this relation. Okay. So maybe I should. So we were given this relation. Ak plus 2 equals to 5 times Ak plus 1 minus 6k. Now once we have that, so by inductive hypothesis I know that this Ak is equals to 2 power k plus 3 power k, and Ak plus 1 is 2 power k plus 1 plus 3 power k plus 1. So we can plug it there, and what we get? We get that Ak plus 2 is 5 times this Ak plus 1, this value, minus 6 times this Ak. And now a little bit of arithmetic will show that if we take this 2k out, 2 power k out, we get 2 times 5 from here, which is 10, and 6 from here. So 2 power k times 10 minus 6 plus 3 power k, and then 15 in 3 from here, 5 from here, 15 minus 6. And which, as you can see, this is equals to 4, and this is equals to 4, and this is equals to 9. So we have this is equals to 2 power k plus 2 plus 3 power k plus 2, and hence Ak plus 2 equals to 2 power k plus 2 plus 3 plus k plus 2. Thus we have the proof that Pk plus 2 is correct, assuming both Ak and Ak plus 1 is true. So using induction hypothesis and this particular version of it, we have been able to prove this particular sequence problem. Now this problem is just one of the examples of what is we call as recurrences, where we are given some term in as a linear combination of its lower terms. Now as you can see, I can also have a problem where I can define an plus 3 as an plus 1 plus an plus an plus 2. In that case, we would have to use some other induction hypothesis. In particular, we will have to use the induction hypothesis where, assuming Pk plus 1 and Pk plus 2 is correct, prove that Pk plus 3 is correct. So we have seen a few of the induction versions of this mathematical induction. While this is just a finite collection of them, one can come up with a lot of other variants of induction hypothesis. The idea is simple, that if you write down in the real line all the possible points for which you have to solve Pk, somehow ensure that you will be able to prove all of them one by one in some way. And this gives us the particular problem or particular way of writing this induction hypothesis. So this brings us to the end of this video lecture. In the next video lecture, we will be looking at some more generalization of this mathematical induction.